Okay, everybody, welcome back here. In this next lesson, we're going to take a look specifically at chemical reactions and heat energy. This applies to combustion reactions, but really it can apply to any chemical reaction, regardless of type. Now, the first item here, recently, you've looked at combustion reactions, and this is a specific reaction usually involving molecules where a fuel molecule reacts with oxygen to produce carbon dioxide and water. That's a combustion equation. Now, what we're going to look at in this lesson most certainly applies to combustion, but again, it can apply to any chemical reaction. Okay, so we can talk about chemical reactions in terms of heat energy. What is heat? It's this, okay? Heat is a transfer of energy, what's called thermal energy, from one system to another. Now, system is just a really fancy way of saying an object, okay? So heat is when thermal energy goes from one thing to some other thing. When you pick up a hot coffee mug, thermal energy is going from the coffee mug into your hand. And that happens because of a temperature difference, okay? And you got to keep in mind that temperature and heat are different things. Temperature, remember, is just the average motion of the atoms and molecules something is made of, okay? Heat is the total amount of energy in the object, okay? So heat depends on mass. Temperature doesn't, okay? And generally what happens, and you can see here, actually let's get a pin. There we go. Thermal energy, we'll bring that up, goes from whatever the hot thing is to whatever the cold thing is, okay? And think about it. If you put a cold glass of water out on a table on a very hot day, eventually that water gets warm because energy is going from the warm air into the cold glass of water, okay? So that's heat. Now, when we talk about chemical reactions and heat, we have a couple terms that you need to know. The first one is what's known as potential energy, okay? This is the energy stored in the molecule. So whenever the chemical bonds are in a molecule, the energy stored in it is potential energy. Let's say you get some gasoline for your lawnmower and you put it in one of those red containers, okay? That gasoline isn't burning, but it has the potential to do so. It has a lot of energy stored in it. That energy is potential energy, okay? Now, an intermediate is kind of a technical thing. It's a temporary molecule or thing that forms. It's a transition state when a reaction goes from the reactant molecules to the product molecules, okay? So when chemicals are reacting, there's a very temporary state where all the atoms are kind of, mushed together into this very temporary thing, and we call that an intermediate. It doesn't last for very long, a fraction of a second sort of thing here, okay? But that's the intermediate. We also have activation energy, okay? This is the energy needed to start a reaction, okay? Or when we look at the graph in a moment, it's the energy needed to get over the potential energy hill. So for instance, if you want to light a candle doesn't just burn on its own. You need a match to light it. The energy from the match is activation energy. There's also what we call heat of reaction, signified here with triangle H. It's actually a Greek letter. That's heat of reaction. This is the energy that's either released or absorbed during a reaction, okay? Again, in a moment when we look at some graphs, it's the difference in potential energy between whatever the reactants are and whatever the products are. That's the heat of reaction. So from start to finish, this is the heat that a reaction either gives off or absorbs. We also have catalysts. A catalyst is an element or molecule that allows the reaction to happen more easily, okay? And what catalysts do, in some way, they lower the activation energy. So technically, a catalyst doesn't speed up the reaction, It just makes it easier for the reaction to happen, and then the reaction happens more often. Okay? They lower the activation energy. They make it easier for that intermediate thing to form between whatever the reactants are. So that's a catalyst. In your car, there's a catalytic converter in the muffler in the exhaust system, and that converts carbon monoxide to carbon dioxide. And it allows it to happen a lot more often than it would otherwise. All right, what else here? So now we come to the graphs. This first graph is what's called an exothermic reaction. Okay, so and some features here on the y-axis, potential energy, x-axis is time and the progress of whatever reaction we're dealing with. Over here, this represents the energy stored in the reactants, whatever you're starting with. And over here, this represents the energy stored in whatever the product molecules are. Okay? So the question, how do they compare to each other? Take a moment and answer that. Hopefully you said this, the potential energy of the products is less than the reactants. Okay? Next question, where did it go? Where'd that energy go? Where did it go? So energy can't be created or destroyed. We've talked about that. So the energy, the difference, went out from the reaction. It left the reaction and went out into the environment. So imagine if this is like firewood we're burning, that produces light and heat. The difference between the blue line and this red line, that amount of energy is what was released in the form of heat and light during the campfire. Okay? Some other features of the graph. Again, the difference between the blue and the red, we call heat of reaction. That's the heat that was released during this reaction, whatever it was, burning wood, burning gasoline, burning a candle, whatever the case may be. Okay. Notice here, this hump is the activation energy. So we start here in the reactants. We have to add some energy. In this line, the black line represents energy as the reaction happens. This hump is our activation energy. We have to get over that. And once we're here, the reaction just then begins and it happens on its own. And this energy is released. And then we're left with products with this much energy. Okay? So this difference is the heat released during the reaction, during an exothermic reaction, where heat is leaving the reaction. And this is the activation energy, what we need to add to get the reaction started. This is an endothermic reaction. Endo means within. So this is a reaction where heat is absorbed during the reaction. So the next question, again, reactants, products over here, how do they compare? The answer, the products have more energy than the reactants. Okay? And you read this graph the same way. Y-axis, potential energy. X-axis is the progress of the reaction, how quickly, how it's happening. Blue are the reactants, and the red here are the products. Okay? Products have more energy than the reactants. And again, just a reminder, reactants are what you start with in a reaction. Products are what you end with. Next question, where did this energy come from? So the rise in energy, the difference between blue and red here, it's energy that went into the reaction, probably from whatever the activation energy was, which could be light or heat or friction if you mix something, a spark, etc. Okay. So on our endothermic graph, again, this is the energy of the reactants. The red is the energy of the products. We start here. We have to add all this energy, this activation energy, to get the reaction started. Once we hit this point, then the reaction happens on its own, and some of that activation energy is absorbed by whatever the product molecules are. That's our heat of reaction, which in this case is absorbed into the reaction. And examples of this, if you've ever used a chemical cold pack, that's an example. When you make the cold pack work, there's a reaction, and that reaction is absorbing heat from the surroundings, including whatever part of your body you put that cold pack on. Photosynthesis is also an example of this. Plants make sugar. Some of the energy from sunlight, activation energy, is stored in the product of sugar. Okay? Endothermic, again, is a reaction that is absorbing energy in some way from the environment. Okay, so any chemical reaction we can describe in terms of how it either is releasing heat or absorbing heat from the environment. All right, folks. Along with this video, there's a PDF file in Google Classroom. Take a look if you need to review, and I'll see you next time. All right, thanks, everybody.